Well, so for the next one, if you hear Daryl Irvine, you will have to accept me as a cheap substitute. Daryl couldn't travel here because of a personal reason, and so I've been asked to, if I want to give a quick talk, and then based on what Anil just said, I thought, so I'll pick up on the global theme because I recently came back from an OECD meeting in which, I was asked to talk about nanomaterials specifically in terms of the safety, a new concept that has developed in the world of chemical safety, namely adverse outcome pathways. And so, as a brief introduction, we thought that when the advent of nano, that there's going to be a very well-organized risk characterization assessment of these materials through all the classical pillar stones, but it was much more haphazard. Lots of data were developed, but it has not been systemized, and as a result, there's often you hear the statement that we do not have a good system in place to evaluate nanomaterials. And this problem was also compounded by the fact that nanomaterials developed at such a rapid pace that where the attention was, on pristine nanomaterials, that all these derivatives have grown out of it in what quickly became a transition in which nano industries per se didn't develop, but nanomaterials through nano intermediates made available the development of a huge number of nano-enabled products. So I liken it to, while running after a train, that train in the time period that we looked at it is now a totally new object sliding through the Swiss Alps in a three-dimensional model. And part of the excitement of nano and part of also the complexity of nano was also then reflected in the fact that nanomaterials became available. They had intrinsic properties such as the purity, the chemical composition of the material. They acquired a new set of extrinsic properties when they come into contact with biological fluids, acquire a protein corona, dissolution, etc., so that this determines a whole set of interactions at the nanobio interface, and the sheer complexity of that led to a lot of debate, and people actually never defined a necessary set of minimal criteria, although we tried very hard through various different journals. But what I will try to tell you now, that out of this complexity, nonetheless, there is a possibility to do some structure-activity relationships to ease up somewhat on this complexity. And this was done, amongst others, by our Center for the Environmental Implications of Nanotechnology. There's a 10-year funding in which, right from the start, we created nanomaterial libraries. We set up high-throughput screening processes that were based on various biological discovery programs to cover the interaction from molecular targets through cellular systems to organ toxicity. Okay? And I'm going to show you that I think embedded here actually is a paradigm that could be used for the safety assessment of nanomaterials. Now, concurrent, while this is happening, in the world of industrial chemicals, 80,000 industrial chemicals, fewer than 1,000 that had ever undergone proper scrutiny, came the realization that if you want to do this exercise and catch up with the backlog, that there actually is, across the literature, a lot of data that have been collected that you could string together in a concept that is known as adverse outcome pathways. And an adverse outcome pathway combines information from multiple fields of inquiry to illuminate knowledge of biological pathways, highlight species differences or similarities, identify research needs, and support regulatory decisions. And particularly from regulatory decision, an adverse outcome pathway is a structured representation of biological events leading to adverse effects and adverse outcome that can be used for risk assessment. The AOP links existing knowledge from molecular initiating events through a number of testable key events to this adverse outcome. And the beauty is that you do not have to do this ab initio for every new material or chemical that you study. A lot of the information is already available. It only needs to be linked together appropriately. And then, importantly, from a standpoint of then taking action on this, out of the AOP continuum, which you can do correlative, qualitative, semi-quantitative, quantitative, etc., is the ability then to define integrated assessment approaches, which are pragmatic, science-based approaches for chemical hazard characterization that rely on the analysis of existing information coupled with the generation of new strategies. And the types of decisions that you can reach through the AOP test platforms, you can prioritize, you can do read-across, hazard identification, predictive toxicology, risk assessment. So all of this is within reach. So what is the evidence that this paradigm actually can apply? And the two best examples at the moment are in the world of endocrine disruptors, and the other is in the assessment of cosmetic chemicals, where it's well known that cosmetic chemicals, when they cause certain skin sensitizations, which is an immunologically based platform where electrophilic chemicals covalently couple to skin proteins, which are presented by keratinocytes to dendritic cells, and once T cells are activated, it leads to skin sensitization, and it's not necessary for every new chemical, if you have a question, to go through the entire list. The current thinking is that if you have a key event test for the peptide reactivity, a key event for the keratinocyte oxidative stress event that leads to immune activation, or a test for an antigen-presenting cell activation assay, that decisions could be made, for instance, from the first KE1 and the KE2, if you test, if both are yes, you have two concordant results, which could lead to a decision not to proceed, to include that chemical. If the answer to the first one is no, then a suggestion is that another test, the KE3, will be able to help you make that decision if you have two concordant answers. So from this perspective, with the world of nano and all the complexities that I've spoken to you about, I think that we have, through our high throughput efforts, derived at a number of places where you actually can now apply this paradigm, and I will give you two examples. The first is for high aspect ratio injury materials, and the second one is for tiered oxidative stress effects. So let me turn to the high aspect ratio. This was then an idea set that was developed. How do we assess carbon nanotubes? Carbon nanotubes come in all sorts of varieties, single, multi-wall. They have different aspect ratios, stiffness, charge, chirality, etc. The test system that had evolved through high throughput screening is that, from a perspective, if you want to look at worker safety and lung injury, the paradigm is that the long aspect ratio of the material plus its surface reactivity define two key events, namely bioavailability at lysosomal level and catalytic injury to the lysosome, which activates the NALB3 inflammasome, leading to interleukin-1 beta production, and that subsequent to macrophage activation in the intact lung, the interleukin-1 beta plus the carbon nanotube interaction with the bronchial epithelium leads to a process of mesenchymal differentiation into fibroblasts with the secretion of TGF-beta, and this march of events can be studied in cells and faithfully reflect this march of events that occurs in the intact animal lung. And just to show you very simplistically, in a library of nanotubes, a crude tube, a tube that had a surface carboxyl or pegylation as compared to a tube with cationic charge, amino and polyethylene imine, you can see that as one test, a test that defines injury to the lysosome, and that is the release of cathepsin B into the cytosol. The crude tube was very active. That correlated at cellular level in macrophage culture system with production of interleukin-1 beta. In a co-culture with macrophages and epithelial cell that correlated with a similar display of TGF beta production. If you had tubes that were surface passivated, this effect disappeared, the interleukin-1 beta level disappeared, and if you brought back cationic tubes, again, toxicity reappeared. This was reflected in the in vitro studies and faithfully reproduced in the animal studies, so giving you the ability to classify a lot of nanomaterials by a AOP, which would have as molecular initiating events the carbon nanotube characteristics damaging the lysosome, a KE1 interleukin-1 beta, a KE2, the events that lead to the pro-fibrogenic growth factor production. And as I've shown you, the AOP could then be used for decision making. One decision making, as I've shown, was that you can take the in vitro screening to show that you can do tier 2 testing in animals. And this was all done to try and prevent the use of a test that was often asked for $500,000 to $1 million to do a 90-day inhalation study. And through a combined group with industry, people from government agencies, we at least tentatively agreed that if you can now use an IATA, based on this, you can ask a set of questions, says, is this carbon nanotube of concern to humans? If the answer is yes, is it inhalable? And if, next question, is there exposure potential in the workplace or consumer? If the answer to both questions are yes, then data are needed. And what type of data will you collect? Well, you can do the tier data, but if you don't want to use animals at all, the AOP-based approach is appropriate. And just to show that, how appropriate it is, from a set of carbon nanotubes, it was collected randomly around the world, including 2 that went through this very expensive test system. After 90 days, people could say, listen, yes, we do have macrophages, lymphocytes, neutrophils, and IL-1 beta in the lung. Compare that to the paradigm that I sketch out for you, where with one single test, we could compare these materials and could line them up with a predictive outcome that could easily be tested. Another quick example is that you could use tiered oxidative stress to characterize a lot of materials. This has been done by a system that then developed. Nanomaterials frequently cause oxygen radicals, and it's not a random event as to what happened. The oxidative stress can assume 3 different tiers: antioxidant effects, inflammation, and it depends on the redox shuttles in the cell that communicate with the nanomaterial so that there's progressive flow of electrons and adverse outcomes that could be deliberately studied. I'll show one material that is a metal oxide. The metal oxide is doped so that there is a band gap that overlaps with the energy levels collectively of all the redox shuttles. As you do more and more doping, more electrons are bled from this interface, leading progressively for this material with incremental doping to make more oxygen radicals, and this then leads to a tier 1 event. If you cross this barrier, progressive production of interleukin-8 production, and ultimately in the animal lung, the same inflammation and neutrophil count is a reflection of the IL-8 equivalent production. So from this particular perspective, we could then group materials. We could characterize them between transition metal oxides that have band gap overlap, that don't have soluble materials. New categories of materials could be introduced that had their own way of causing cell danger. I don't have time to go into this. This ultimately evolved into doing a group of 70 to 80 different metal and metal oxide nanomaterials for which we have the molecular initiating events for the whole series to study. We have the intermediary key events to do select testing on, and being able then to very rapidly put a whole category of materials. So this, for instance, is a recent attempt to take these materials and do a screening for the different metal oxide categories for AOP liver damage, in which a lot of information could be derived in how to screen and how to build new systems to affect the liver. And I don't have time to go into those details. So what I have not told you, and where this paradigm still does not fit in, and that is into our nanotherapeutics efforts, because of essence, our physical-chemical characterization in vitro and in vivo studies are all driven by a preclinical study process to conserve physical-chemical characteristics of the new drug, in addition to the impact on PK, biodistribution, ADME, dosimetry, and possibly unique hazard. But where I do see in future a potential for the idea set to advance itself, and I deliberately chose what Professor Jules Hoffman said this morning, is to introduce you now is where I take redox active metal oxides. I take the concept that cancer cells by certain chemo agents can be induced to undergo a form of immunogenic cell death where they process by antigen presenting cells while also inducing immune stimulating adjuvants. So we have in pancreas cancer developed a system of nanocarriers that I will talk about on Wednesday, where we have defined a chemo that will induce all of the tiers of the cell death event. And if I now take you to a screen of redox active nanomaterials to define materials that can at cellular level induce this form of cell death, I can show you there are 4 materials. The rest did not react. If we took materials 1 and 2 that did induce the immunogenic cell death events in cells and used it now in a pancreas cancer model in mice, you will see the chemo agent, material 1 and material 2, could effectively reduce those tumors, while the metal oxide that was non-active had no effect. And we could prove that this effect is driven by the immune system by studying for instance, the appearance of CD8 T cells and disappearance of regulatory T cells, so as to, for material 1 and 2 to constitute an increase in CD8 Treg ratio. So I will stop here and take one question and just thank the work that was done by a multidisciplinary group in the University of California Center for the Environmental Impact of Nano. Thank you. Happy to take one question.
Hi, thank you very much. I'm from National University of Singapore. I would like, it's more a curiosity, I would like to know your opinion on that. With the fact that with cosmetics there is the banning of animal testing, and on the other hand, the OECD guidelines, to my understanding, they provide some testing, like the direct peptide reactivity assay, that might not recapitulate the full skin sensitization. My question is, how can we ensure that products that are nano-based are safe to the consumer? Because we can't do much of testing.
Well, you know, so I would say we will have to present data. And in the US, the law has now changed. There's mandatory data needed. So what type of data are you going to present? For non-cosmetic materials, animals have not been banned. And I personally don't think that animals are going to disappear immediately. I think it's going to be...
I'm specifically for cosmetics.
You know, specifically for cosmetics, I think that the AOP-based concept and the methods being developed, as demonstrated here in the sensitization assay, are probably those that will endure. The question is, for each of the potential cosmetic side effects, do we have an appropriate test? And I'm not sure that we have a full display of non-animal tests.
Thank you.
Okay.